Hi, it's Annalie again. Today I'm in Glasgow speaking with Jim Hough, who has spent his entire career designing and building gravitational wave detectors. He has spent almost 39 years in this field and is one of the key leaders in the international teams that work on them. Hi Jim.
Hello Annalie, it's very nice to see you.
Nice to see you too. So 39 years and you're still waiting for the first detection of gravitational waves.
Yes.
Are you starting to regret getting into it?
Not at all. I've had a most enjoyable life working in the field, solving lots of different problems in lots of different areas of physics that were relevant to the detectors that we were making.
So if you're enjoying the figuring it out, it's like a bit of like a puzzle, could you say?
Yes, it's very much like a puzzle. You know, you solve one piece of it, then something else doesn't work and you've got to solve that piece.
Right.
And what has been so exciting is that we've had to use really our knowledge of almost all fields of physics to solve the problems.
But if I knew when I started that this puzzle might take me over 30 years to solve, I would maybe consider a different puzzle?
No, not in my case. I knew it would take a long time, but there were so many interesting and challenging sort of facets, you know, that we had to face up to. So it really has been most exciting, and I've never regretted it for a day.
So what exactly is a gravitational wave?
Well, it's almost like any other type of wave. For instance, if we throw a stone into the water here, you see water waves spreading out. Now, what gravitational waves are waves in space-time. Now, I know that's a difficult sort of thing to explain, but they're waves that are caused by mass accelerating very hard. When we go over and sit in the power sports car and we can accelerate away, we will be generating some gravitational waves, but they will be very weak indeed. And to get reasonable strengths, in fact, of signals, we've got to really look out into the heavens, look out to astrophysical sources where huge amounts of mass are accelerated very hard. Right. Maybe supernova explosions or other kind of rotating and coalescing stellar systems. Right. So we can't make gravitational waves on Earth, unfortunately, at least not at a level we can ever detect. But we do know they exist and that they're coming all the time, coming towards us on Earth from outer space.
We are now in the University of Glasgow, stood behind Lord Kelvin's very own desk, next to Lord Kelvin's very own experiment. So I've been told you hold the Kelvin chair. What does this mean?
Well, it's one of the named chairs in the University of Glasgow, and I'm very proud indeed to be the holder of that. Because Kelvin did a vast amount introducing new technology, having new ideas in physics.
Wow.
Kelvin was a true experimental physicist, doing a whole range of experiments and developing new techniques. For instance, he was responsible for the first working transatlantic telegraph cable. He also conceived the idea of an absolute zero of temperature, and he designed lots of instrumentation. And just one I should mention is a siphon recorder for the telegraph cable, which recorded the tiny voltages and turned them into mechanical movement that came out. In particular, the siphon recorder put the mechanical movement onto a piece of paper with ink, and with ink that's electrostatically charged, and that is the idea behind the inkjet printer today. So in a way, Kelvin invented the first inkjet printer. So
Kelvin has in some way influenced the new technology development that you're into?
To a large extent, yes. Kelvin's thinking has influenced us, because Kelvin always said you couldn't believe anything until you had measured it. And that's exactly what we are trying to do with the experiments to look for gravitational radiation. We want to measure the signals. For instance, he set up this glacier about 120 years ago, and it's still operating.
So how does this one work exactly?
Well, he started off with placing some tar, I think, like you get in the road at the top, and he has just been watching it, or we've always been watching it for this time, slowly descend like a glacier. And it just shows that pitch or tar is a viscous substance, as is glass, for example. So you're just waiting for it to continue on? Eventually, it'll take a long, long time. It will all reach the bottom.
Wow.
And in fact, it demonstrates the fact that to do really difficult experiments in physics requires a great deal of patience. And that's what we are finding in the development of the gravitational wave experiments.
So how did you get into the research?
Well, I got into the field about 1971 because there had been a physicist in the US, Joseph Weber, who had made a simpler form of gravitational wave detector in which he had just had a bar of metal, and he looked for the bar being pulled out and let go again. And he had a number of these bars set up at different points in the US, and he found that the bars were excited. They seemed to be excited at the same time, as if something had come in and affected all of them. And he deduced that what had come in were gravitational wave signals.
Okay.
And so there was so much excitement caused by this that a number of research groups around the world were set up to repeat Weber's experiments, or to extend them, in fact, mainly, and to see if they could see the signals also. Right. And one of these experiments was set up here in Glasgow by Professor Ron Drever, who was here then, and I joined him in these first experiments. Right. And then following on that, we didn't see any signals. Nobody saw any signals, and it was realised that probably signals were weaker than people had expected in the very early days, and that it needed better detectors. Right. And the obvious way to make better detectors was to move the kind of masses further apart, the two halves of the bar further apart, and to use laser light to monitor the motions of the relative motions of these masses. Right. And that's really how I got into the field.
Right. So what have been the major milestones for you during the 30-odd years you've been working on this?
Well, the first milestone was actually making the bar detectors work and getting the kind of displacement sensitivities that were needed at that stage, and that was a real step forward, because people then didn't think that one could measure the tiny distances, that were required. Then the next milestone was that in Glasgow we built an optical interferometer, a prototype interferometer of the type here, but with the arms only 10 meters long. Oh, wow. And then it was when we got that interferometer to measure displacements that were about a millionth of a meter between the arms, that we realized if you scaled this up to the big, much longer arm lengths we now have, that it should be possible to detect gravitational waves. Again, people thought that was not possible, and it was wonderful to show that it was. Yeah. And then that milestone here, and also in Germany, with an equivalent group doing the same sort of thing, and then a group in the US showing the same, it was these measurements that allowed or encouraged the big laser interferometers to be built. Then another milestone was when at last we got funding to build the detector in Germany, GEO 600, because there was quite a struggle in persuading people that it was worth building such instruments. And now, I suppose the last major milestone has been that GEO has been working very well, and in fact all the gravitational wave detectors worldwide have been working very close to the kind of design sensitivities that were required of them.
So how exactly does a gravitational wave detector work?
Well, a gravitational wave detector works by really producing forces on objects which are a distance apart, what's called a strain in space. So if you have two objects, like an object here and an object here, if a gravitational wave comes down like this, it will make these objects move apart and come together again by a tiny amount. Okay. To measure that kind of movement, the best idea is to use laser light and to put in a third mass here. And the nature of gravitational waves is such that when it makes one distance here extend, the other distance will compress. So it will cause a differential movement between the two arms. And so what we do is to bring in laser light like this, shine some of it up to a mirror on one arm and then back again and out of the system. Some of the light comes this way, it comes back, and it joins, it adds to the light that came from the first arm, and by looking closely at the property of the intensity of the light here, it is possible to measure relative movements of these masses. But these masses have to be very, very free indeed. So they're hung as pendulums and need to be very special pendulums.
What are the biggest challenges you face building, designing and detecting the
Well, I think the main challenges are, first of all, hanging these masses as pendulums in such a way that noise is minimized, what's called thermal noise is minimized. And also we've got to make sure mechanical vibrations don't get into the system. And that's in fact why we use pendulums, to give this freedom from the surroundings.
Right.
But also looking at making the mirrors at the ends good enough to reflect all the light that goes out in order that it comes back again with virtually no change. That is also a major challenge.
Well, because this relies so heavily on new technology, do you have an idea for when it'll be ready to detect?
Well, we have never thought that really with the present detectors that we would reliably see gravitational waves. These were just sort of initial detectors in a sense to develop the technology. But now we know that if we take the technology of using the silica fibers, if we take that technology and put it into the US detectors, the LIGO detectors, to form advanced LIGO, that these detectors, when fully built up, will almost certainly see gravitational waves. And our colleagues in Italy are doing the same with the Virgo detector, using the silica fiber technology also. And we think that by about 2016 or 2017, we should be able to make our first detections in a reliable way.
So quite soon then?
That is relatively soon, given the time and fact that we've spent doing it.
Exactly.
It's a little bit like the pitch experiment, you know, one has to be patient and let it continue.
Right. Why are you so keen to detect gravitational waves? What will we learn from that?
Well, the existence of gravitational waves really are perhaps the one prediction from Einstein's general relativity that has not been experimentally proven. And as Kelvin said, you can't believe something until you've experimentally measured it. But also, gravitational waves come from far out in the universe, from, for example, two small black holes coalescing and merging maybe to form a bigger black hole, or other interactions of neutron stars and black holes, just as an example. And really, using these signals, we hope to start a new astronomy.
Are there lots of people working on this? Are they big groups you work in?
Yes, well, I mean, the GEO collaboration is probably more than 100 people now, whereas the LIGO scientific collaboration and Virgo, who are kind of becoming close to that, there are more than 1,000 people altogether.
And is it exciting working in big groups like this?
Oh, it's very exciting working in big groups because everyone has their own part to play. Inside the big groups there are subgroups and we all feel ownership for the things that we do. For example, you'll find that Sheila Rowan feels real ownership in providing the very delicate silica suspensions for advanced LIGO. And it is really very exciting to work in this kind of area. It's not just work, you know, it is a way of life. That's what we do. I mean, that really is what drives our whole life, in fact, contributing to these big experiments.